Hi Bobcats! This video is going to introduce the concept of hybrid orbitals. Hybrid orbitals will allow us to match up the geometries that are predicted by Vesper theory with this concept of orbital overlap from valence bond theory. The bottom line is that the structures that are predicted by Vesper theory are a pretty good match to experimental observations. When we go in and measure bond angles on something like methane, experimentally we determine it really is about 109.5 degrees. So the problem with valence bond theory then is that we need to somehow overlap orbitals that are going to be oriented at 109.5 degrees to one another. Well, s orbitals are spherically symmetric, they're going in all directions. P orbitals, if we talk about a subshell of P's, we have 3 p orbitals that are all pointed at 90 degrees to one another. That's not 109.5. So somehow we need to create some orbitals that are oriented at that 109.5 degree bond angle. So these hybrid orbitals are going to fill the bill. For those of you all who love math, you'll like this first line. The mathematical process that we use to create hybrid orbitals is we are going to take linear combinations of the wave functions that define the s, p, d, and possibly even f orbitals. That's like really advanced math, like graduate level math. So let's look at this from a little bit more conceptual side of it. Think about it this way. We're going to create some sort of an average orbital where we're going to average maybe an s orbital with a p orbital, or average an s orbital with a couple of p's. These averaged orbitals are going to follow some rules, such as when we do this hybridization or this averaging process, if we start with 3 atomic orbitals, remember atomic orbitals are the s, p, d, and f ones. If we start with 3 atomic orbitals, we're going to end up with 3 hybrid orbitals. So however many orbitals go into this process, we're going to have that same number coming out. And the reason that this works is because we're going to end up in a lower energy situation when we can place electrons into the hybrid orbitals that are at a lower energy than they are on their isolated atoms in their regular atomic orbitals. Then we're going to form a bond, right? Because bonds form because it allows the whole system, the electrons and the atoms, to reach a lower energy situation. And it turns out when we do this process correctly, the hybrid orbitals that we produce line up with the geometries predicted by Vesper theory. I'm going to start by trying to show the hybridization process that results in the tetrahedral geometry. What we're going to do, since we need 4 orbitals to point towards the corners of a tetrahedron, is that we're going to have to take 4 orbitals to hybridize or mix together. And so what we'll do is the first of those orbitals will be an s orbital. We always start with s. And then we'll also take a p orbital, that's orbital number 2, another p orbital, that's orbital number 3, and then finally the third orbital from that p subshell, which is the 4th orbital for our hybridization process. When you crunch the math on this and you create this set of 4 hybrid orbitals. These 4 hybrid orbitals are all exactly the same shape. Now when you look at the shape of these green hybrid orbitals, the nucleus is where this little node is. So the nucleus sits right here. And then when you stick all 4 of these hybrid orbitals onto the nucleus at the same time, that's what we get in this last structure. The major lobes of these orbitals point towards the corners of a tetrahedron. And this is kind of backwards to how I usually draw a tetrahedron. So we have the plane line going straight up, and now this time the plane line is going to the left. Then there's a wedge down and to the right and a dotted line down and to the right. That's kind of the mirror image of how I normally draw the tetrahedron. Because we took one s and three p's, this type of hybrid orbital is referred to as an Sp3. This means that there's one s and three p's involved. The number of orbitals in this hybrid set is 4. Because we took 4 orbitals to hybridize, we get 4 hybrid orbitals out of it. When we look at energy level diagrams, by the time you hybridize the s orbital and the 3 orbitals in this p subshell, the hybrid orbitals end up a little bit higher in energy than the 2s, but a little bit lower in energy than the 2p. So overall, if we're going to have 4 electrons in here, which is, this is describing the bonding in carbon, by the way. When we put those 4 electrons, 1 apiece in each of these hybrid orbitals, that's overall going to be at a lower energy than the electrons on the atoms in these on the atom in these atomic orbitals. I'd also like to show what happens here to try to explain the trigonal planar geometry. For the trigonal planar geometry, we need 3 hybrid orbitals that are pointed at 120 degrees from one another. Well, if we need 3 hybrid orbitals, we have to start with 3 atomic orbitals. So here are the 3 atomic orbitals. 1 of them is an s and 2 of them are p's. And that leaves us a single unhybridized p orbital. Why is that important? Why am I bringing that up? Well, it turns out for something like carbon, when it has this type of hybridization, which is called Sp2 hybridization, that collection of 3 hybrid orbitals and then this one unhybridized p orbital allows that carbon atom to make a double bond. The second bond of the double bond will be formed from this unhybridized p orbital, and the first bond in the double bond, the sigma bond, will be formed from one of these hybrid orbitals. But this process of creating Sp2 hybrid orbitals gives us a collection of 3 hybrid orbitals plus 1 unhybridized p. And the last hybridization scheme I want to take a look at is the hybridization scheme that we use to explain linear geometry. If something is linear, if a molecule is linear, it's going to have 2 atoms arranged around that central atom. And so that means we need 2 hybrid orbitals pointed at 180 degrees from each other. 2 hybrid orbitals mean that we need 2 atomic orbitals. So we'll take 1 s and 1 p. That leaves 2 unhybridized p orbitals that can be used for pi bonding. So that allows the molecule to use the hybrid orbital for the sigma bond, and then possibly do 2 more pi bonds for a grand total of 3 bonds, or a triple bond. So when we hybridize the s and the p, we get 2 sp hybrid orbitals, plus we have these 2 leftover unhybridized p's, and then this last diagram is showing all of those stuck together on the atom. So we have the hybrid orbitals shown in green, and then those 2 unhybridized p orbitals perpendicular, all perpendicular to each other. I'd really like for you to take a moment right now and look at section 11.3 in your textbook. The animations that they have in there show how you take these hybrid orbitals and overlap them to get sigma bonds, and then they they show very clearly how those unhybridized p orbitals are available for that side-to-side overlap to make pi bonds. And those diagrams, those short little, I mean, these are like 5-second animations. Those animations just do a really good job of showing how all of that stuff fits together. So please take a moment and go and look at those.